Okay, so I forgot to show this over here. And this is what determines polarity. So this is what I just talked about on the last video real quickly. So here you go. Okay. Right, now we'll continue with interactions. So now we're going to see why polarity makes a difference in terms of interactions. Again, use your notes. We did cover this. Okay, so molecular interactions are when molecules interact with each other. And if you have a solid, all the molecules interacting with each other. If you have a liquid, some of the molecules are in interaction. And if you have a gas, none of the molecules are interacting. Okay. So, first of all, polar molecules. Polar molecules have plus and minus ends. So they can naturally just line up with each other, where the plus will line up with minus, and that's called electrostatic attraction. And that type of interaction between polar molecules is called dipole-dipole. And water is a real good example of that. Water has a plus and minus end on it. It's polar. Plus end of water interacts with minus water. That's why water is a liquid and can form a solid because of that. Anything that dissolves in water is polar. That's because polar things like each other. They just line up plus line up with the minuses. So since anything that dissolves in water is polar, that's because water is polar, we say that polar things are hydrophilic. Which means love water. Now, we just call it that, but so hydrophilic is kind of another name for polar. That's because all polar things dissolve in water. That's because water is polar. Okay, non-polar molecules are different. Now I gave you a list of it, and I went through carbon dioxide and dry ice. They don't have a natural ability to connect with each other because they don't have a natural plus and minus. But they can be forced to get one. They need help, and I went over that, talked about the nerdy idea. Okay, once they get a help to form interactions, they form what we call London dispersion forces. And then when you do form them, they form very, very strong. Okay. Finally, what happens when you put polar and non-polar together, like oil and water? So oil let's see, make sure I did this right. Okay, oil and water. Now this is non-polar, and this is polar. And we all know what happens when you put oil and water, they don't mix. And the reason they don't mix is the first thought is, well, they're different people. So one people say, well, oil is less dense and so it floats to the top. That's not it, okay? Another way of thinking is, oh, oil and water don't like each other. And that's kind of the way that's usually talked about. They separate, and the way that we basically explain it is oil doesn't like water. So we say it's hydrophobic. Okay, so non-polar things don't dissolve more but water, and we kind of suggest that they don't like each other. Well, that's not right. And this is important because it explains why soap works and etc. When you put oil in water, what happens is the water molecules, and when you take oil, you drop it in the water, what happens is the water molecules are attracted to each other. And so what they do is they like the water, other waters really well. And what they do is they push the oil molecules together into a ball. Not because they don't like the oil, it's because they like themselves. And then when they push the oil molecules into a ball, they got pushed. Okay, I said that was one of the ways you can increase London dispersion forces by adding force. They're increasing their interactions because there's more of them all connected together. So when water pushes them together, that actually makes those oil molecules, helps the oil molecules like each other, and they stick together. And increases the London dispersion forces. So when you put oil and water, the reason why they separate is first, water likes itself, so it pushes the oil molecules together. They get to the other water molecules. And in the process, what it does is it forces the non-polar molecules interact with each other to form better and stronger London dispersion forces. And we just saw that with soap. When you put soap and water, the non-polar tails all aggregate together. They get pushed together. When you put phospholipid bilayer into water, what happens is it gets pushed together. The non-polar parts get pushed together. So this is a very important scheme throughout all of structure and biological systems. Okay. So that ends the review for polarity and molecular interactions. Okay, I will piece this together now and put it up on Blackboard, and hopefully it turns out okay. All right, thanks, and we'll be in touch with this.